Okay, in this video we start to discuss section 3.3, properties of functions. Okay. First, we talk about the even-odd properties. Even and odd property. Let's see the definition first. What is even and odd? We already know what is an even number and what is an odd number. Now, let's see what's the even function, odd function. A function f is even if for every number x in its domain the number negative x is also in the domain and f negative x is equal to fx. Okay, so this is the even function. A function is even, an even function. Then what is odd? Let's first give both definitions and we have examples to clear them. A function is odd if the same thing for every number x in its domain the number negative x is also in the domain and okay, the difference comes f negative x is negative f of x. So this is odd. Even and odd. Even function means if you have f of negative x, you can ignore the negative sign. Odd function means if you have f of negative x, you just move negative sign forward. Okay? So let's check it. For example, let's see if we have y equal to x squared. Y equal to x squared. For this function, you see here, whenever you have x in the domain, the negative x is also in the domain, and the corresponding y value are the same. So f negative x is fx. They are both equal to x squared. They are both x squared. This is a even function. And even function, you check that because they have the same height. If you fold this graph along the y-axis, they coincide. If they fold it, they coincide. So it means the graph of the even function is symmetric with respect to the y-axis. If we have y equal to x cubed, let's examine it. if you have x here, then the negative x is also in the domain, and here is a positive. So for example, y equal to negative 2 cubed, y is equal to 2 cubed, 8. Y is equal to negative 2 cubed. It's negative 8. Negative 8 is f. It's negative f of 2. This is f of 2. fx. Name is fx. Okay, you see? This is f negative 2. F negative 2, after evaluation, you see that it is equal to negative f of 2. So this is an odd function. Odd function, you check, it's like the fan. You rotate it pi radian or 180 degrees. You can move this but after rotation, you can move this right branch to the left branch. So if we say the graph is symmetric with respect to the origin. So that's the theorem after the definition and the example. A function is even if and only if its graph is symmetric with respect to the y-axis. So this is an even function because you fold it, because for x and the negative x, since you fold it, they have the same value. 2 points coincide. 2 points coincide. So this is a symmetry about with respect to the y-axis. And a function is odd if and only if its graph is symmetric with respect to the origin. With respect to origin, you just imagine this y equal to x cubed, and when rotate this right branch pi radian, you will get the left branch. So that's the odd function, and actually that's the reason we get even odd. Here's x squared, it's an even power. Here's x cubed, it's an odd power. Okay, you can consider this as the reason behind those two definitions, why it is called even and odd. Okay, so once you have this graph description about even and odd function, it's quite easy to determine if a function is even odd when you see the graph. For example, if you see the graph like this, then you can say, well, assume my graph is very good, then you can say that the function is even because you fold it along the y-axis, those two pieces coincide. And if you see the graph like this, well, it's not symmetric about the y-axis, it's not symmetric about the origin, so it's the function is not even, not odd. Okay, so it's not an even or odd function. And if you see the graph of function like this, let me stretch it. assume my graph is better than this handwriting. This function is an odd function. It's odd because you rotated pi radian, rotated to the left branch. These two graphs is supposed to be the same thing, so it's an odd function. So that's the application, the simple application of the theorem. When you have the graph of the function, you can quickly determine if it is an even function or odd function. And this is a determination based on the geometry. This is a geometry. So the theorem actually says when you have an even odd function, that's algebra, like f of negative x is equal to fx, that's algebra. And if and only if the graph satisfies some property, this is geometry. So this the theorem the theorem connects the algebra with the geometry. When I say geometry, we mean the graph, curves, point, lines, circles, so that they are the geometry. Okay, so this is a straightforward way to determine even odd, but in many cases you don't have the graph, you still just have the formula. So we are going to determine the even and the odd functions algebraically. Determine the even odd functions algebraically. So let's see, there are several examples. X squared minus 5. I want x squared minus 5. Okay, this is the first one. First one, let's check. To determine even odd functions algebraically, we just start from the definition. Okay, so we start from the examination of or computation of f of negative x. F of negative x. Whenever you see x, you write a negative x. So you have a negative x. Because it has a sign, so you have to put a square. Okay, so this is evaluation. X is the input. Now the input becomes negative x. Negative x squared is x squared. 5 is constant. It does not change when you put a negative x or positive x. So x squared minus 5. X squared minus 5. In this place, we do not solve the equation. We actually just compare the result with fx. These two formulas are identical, so you get fx. Okay, so from f negative x, by computation, we get fx. So f is even. Okay, so it's an even function. And second function, fx equal to x cubed minus 1. Let's check. F negative x. F negative x, negative x cubed minus 1. Negative x cubed is negative x cubed minus 1. Well, check here. This formula is not identical to this formula. We do not put them together, solve for x. We should say this is identical to it. So they should have the same formula. Now this is negative x cubed minus 1. This is positive x cubed minus 1. They are different. And also, even you put a negative sign, negative fx is negative x cubed plus 1. Negative fx would mean negative x cubed, and negative 1 is positive 1. So it is not equal to fx. It is not equal to negative fx. It's just a new one. So f is not even, not odd. Not even, not odd. Okay, so it's not even function, not odd function. Third example, h of x equal to 5x cubed minus x. And let's check h negative x. Here. Negative hx. So far, at this moment, we don't know which function we're going to compare with h of negative x. So we write both. H of x negative hx. And then we're going to compute h of negative x. So it's 5 negative x cubed minus negative x. Don't forget parentheses. It's very, very important. Negative x cubed is negative 5x cubed. Negative x is positive x. See, compare this result with one of them. This is equal to negative hx. So h negative x is equal to negative h of x. So h is odd function. Move the negative sign forward, you get odd function. D g of x is opposite value of negative x, opposite value of x, not negative x. Negative g of x is negative opposite value of x. Okay, so g of negative x is opposite value of negative of x, and we know that opposite value sign will kill this negative sign. You put a 2 and you put a negative 2, you do not change the distance between the origin and the 2 and the negative 2. So, and this is equal to g of x. So g opposite value function is even. Opposite value function is even. Okay? So those are the algebraic examination about even and odd functions. Okay, and actually if you sketch the graph of the opposite value function, you can see that the graph is like this. This branch is the diagonal of the first quadrant. This branch is diagonal of the second quadrant. They are symmetric about the y-axis. So it's an even function. It's even. Okay. So this is a even odd property. What is an even odd property? F negative x two directions. If it is equal to fx even. If it is equal to f negative x odd. If it's not equal both of them, either of them. If it is not equal to either of them, it's not even, not odd. Okay, so not all the functions is an even function or odd function. Most of the functions, they are not even, not odd. Okay. Good. That's the first property, and the second property. We talk about increasing, decreasing, or constant property. Increasing, decreasing, or constant. First, let's see this graph. So we have 1, 2, 3, 4, 5, 6, 7, and we have 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 7. 1, 2, 3. Okay, so 2, 3, 4, 5, 6. 6 to 2. -2, -3, -4, -5, -6. This point is -4, -2. This is -4. This is -2. And 1, 2, 3, 4, 4. This is a 0, 4. This point is 0, 4. This is a 4, 5, 6, 7. And then you have a 1, 2, 3. This is 3. And from 3 to 6, 4, 5, 6, 6 is 1 here. So 3, 4, 6, 1. Okay, whatever. This is a graph on page 224. A graph on page 200. When you have some graph like this. Example. The example is about this graph. Where is the function increasing? Where is it decreasing? Where is it constant? Okay, so that's a question. Where is it increasing and decreasing and constant in the graph, from the graph? To answer this question, first we have to define those words: increasing, decreasing, and constant. Okay, so the increasing, when we talk about increasing, we always move from left to right. Okay, so definition. First, we give the definition. A function f is increasing on an open interval I if for any choice of x1 and x2 in I with x1 less than x2, we have fx1 less than fx2. Okay, so this is increasing. Whenever you have a small input, you have small output. Okay, small input gets small output. And a function is decreasing on an open interval I if for any choice of x1 and x2 in I with x1 less than x2, we have fx1 greater than fx2. This is decreasing. It means greater input give you the smaller output. It's decreasing. greater input give you the smaller output. Increasing, you can draw this line and draw this type of curve. You see here, smaller input is on the left side, greater input is on the right side. Smaller output is lower, greater input is higher. So increasing is always this way. Decreasing is like this. Decreasing is like this. So this is increasing. This is also increasing. Decreasing is this, and this is also decreasing. Okay, what is a constant? A function is constant on an open interval. If for any choice of fx1, fx2 in I, we have fx1 is equal to fx2. So with whatever input, I don't care who is greater, who is smaller, they have exactly the same answer. If that happens, you will see that the graph is a horizontal line. The graph is a horizontal line. Then you can see functions are constant. Okay, so with those definitions, we can do this problem. For this problem, from -6 to -4, you see, -6, -4, f is going down, f is decreasing. Okay, and from -4 to -2, from here, we're talking about the domain. It's along the x-axis. So -6 to -4, it's a decreasing. -4 to -2, and -2 to 0. So you see here, the whole thing together is increasing. And between 2 and 3, f is constant. F is constant. And from 3 to 6, f is decreasing again. Okay, so that's the determination. Okay, so that's a way to describe the graph. Here's increasing, that part is decreasing. Okay, so that's the second property, the increasing decreasing property. And property. The first one is the even odd property. It's about the symmetry. Even odd is about the symmetry, and increasing decreasing property give us if the graph is going up or going down. And local maxima and the local minima. Let's talk about the local extrema. What is the extrema? This time let's look at the definition first. The definition of function f has a local maximum at C if there is an open interval I containing C so that for all x in I, fx is less than or equal to f of c. Okay, then we say the function has a local maximum at c, and the corresponding value we call f of c, the corresponding value, a local maximum value. Maximum value of f. Okay, local maximum is a property. Local maximum value is a number, and this is a greater. This is the largest value. Okay, and similarly, a function f has a local minimum at c if there is an open interval I containing c, so that for all x in I, fx is greater than or equal to f of c. This is local minimum, the property. We call f of c a local minimum value of f. Okay, so the smallest value around it, when we say it is around it. From the graph, it will be very clear what is the greatest value around it. It's the highest point. The corresponding y-coordinate will be the largest value. If this point is the highest point in the neighborhood, then the corresponding y value is the greatest value. This is a local maximum. And local minimum, this is local minimum. It's a local minimum, okay? So this is a lowest point. Lowest point has smallest y value. Highest point has the greatest y value, okay? So when you have the graph, you can quickly determine where you get the local maximum and the local minimum. And again, we only focus in the open neighborhood of it. We don't say, wow, over a long line, it is always maximum or minimum. Okay, so let's see the example. For example, we have the graph of function like this. Let's directly have the graph. Okay, so assume this point has x coordinate 1, y coordinate, x coordinate -1, y coordinate 1. So it's a -1, 1. And this point, it is a 1, 2. And this point is 3, 1. Okay, -1, 1, 1, 2, and 3, 1. And based on the graph, you see here, how do you determine the local maximum, local minimum? You just look at it in the narrow domain. If you look at this picture, oh, it's too bad. Okay, if you look at this picture, you see this is a minimum, so it is a local minimum. If you look at this one, ignore other part, just look at this, you get highest point. It says local maximum. If you check this way, it's a local minimum. So when we talk about local stuff, we will cover most of the part. Just focus in the neighborhood, in a small interval. So we can say f has a local minimum at -1. So this is a language. F has a local minimum. This property at -1. The local minimum value is f of -1. We read the y coordinate, f -1 is 1. So the value is 1. And the local f has a local maximum at +1. You see, at the +1 you have a local maximum, the highest point. The local maximum value is f of 1. F of 1, the y coordinate is 2. And 3, f has a local minimum at 3. It's the lowest point. Local minimum at 3. The local minimum value is f of 3. F of 3 equal to 1. Is equal to 1. So we get the answer. You see here, this point is called local maximum, but actually you have even higher point. But those even higher points are far from it. If we only look at the neighborhood, this point 1, 2 is the highest point. So that's a local minimum. Okay. From the graph, you can quickly determine the local extreme. Just check the top point in the neighborhood and the bottom point in the neighborhood. The neighborhood, it has contained the left and right parts. So you see, in the neighborhood, this point is inside neighborhood, not on the boundary. Okay, so like what I emphasized, this point is only the highest point in its neighborhood. There's some other point even higher than this. But check here, any point here, for example, any point here, if you check the neighborhood, it's not the top point, it's not bottom point. So you don't have the local maximum or local minimum at this kind of point. Except, other than the local maximum, let's talk about absolute maximum or absolute minimum. What is absolute? Absolute means I do not focus in the neighborhood. I focus on the whole domain. It is a the top point. Then it's an absolute maximum. If over the whole domain, it's a bottom point, so it's a local minimum. Okay, so that is absolute, not in the open neighborhood anymore. Let f denote a function defined on some interval. This interval may not be open. Here we only say it's an interval. It can be open, closed, half open, half closed, not half open, half closed. So whatever, just an interval. If there is a number u in I for which fx is less than or equal to f of u for all x in I, then the f of u is the absolute maximum of f on I, and we say the absolute value absolute maximum of f occurs at u. Absolute maximum of f occurs at u. So it has absolute maximum, f has absolute maximum at u, the same thing. This is absolute maximum value. Actually, this is again the value. And if there is a number v in I for which fx is greater than or equal to f of v for all x in I, then f of v is the absolute minimum of f on I, and we say the absolute minimum of f occurs at v. Okay, so that's the absolute max and the absolute min. So you have to put this value over the whole domain. So here this I is a whole domain. See, the function is defined over the interval I. So you only focus on this I. That's a domain, a complete domain. And if the value fu is the greatest value among all possible values, that's absolute maximum. If it's a smallest value among all the possible values, is absolute minimum. Okay. So for example, here you can see that this point is the highest point over the domain. Now we only have this domain, and this becomes UFU, the absolute maximum. And similarly, this is a V, FV. This is absolute maximum This is absolute minimum. Absolute minimum. Okay, so let's look at the absolute maximum or minimum based on the graph. If you have the graph like this, so this point is 0, 1. This point is 3, 6. This is a 4, 4. It's a 5, 5. If you have a graph like this, you can see that where is the lowest point. The 0, 1 is the lowest point, and the 3, 6 is the highest point. So we say f0 equal to 1 is the absolute maximum. F0, 1 is the absolute maximum. F3 equal to 6 is the absolute minimum. You have absolute maximum, absolute minimum. Okay, and also you check here. This 4, 4 is a local minimum, but it's not global, since here this point is even lower than this. So it's a local minimum, but not global. Not absolute minimum. This is absolute minimum, absolute maximum, and I draw a circle means this point is missing. From here you can see that if this point is not missing 3, 1 point, the point 3, 1 is the lowest point, it will give us the absolute minimum. But since it's missing, you cannot reach the absolute minimum, and there's absolute maximum 5, 3. So f5 equal to 3 is the absolute maximum, but f has no absolute minimum. Not every function has absolute maximum or absolute minimum on its domain. Okay, so because this point is missing. Okay. Okay, so here you have a 0, 3, and then you reach to this is a 1, 1, 1, horizontal 2, 1, and up 5, 4. So, and then we see here assume this segment is horizontal, then we say f5 equal to 4 is the absolute maximum. And the absolute minimum, every point on this horizontal segment will give us absolute minimum. So fx has the absolute minimum on the interval 1, 2. So every point, because it's a constant. So all the values are the same. They are all absolute minimum value. Okay. And absolute maximum, absolute minimum, they are both called extreme values. Okay, so if you want to just use one word to represent both, they are called extreme values. In the extreme values, one is the absolute max, one is the absolute min. And not every function will have absolute max, absolute min over the domain. So here, this one does not have absolute minimum. They all have absolute maximum, and this one absolute minimum occurs over the whole interval, some whole interval. And also you can see that if we have this function without n, that's a vertical asymptote, then this function has no absolute maximum. And if I put a circle here, f has no extremus. Has no extremus. It has no absolute minimum because the minimum value is missing. It has no absolute maximum because it goes to infinity. There's no maximum value. Okay? No extreme values. No extremus. Okay, so if there's no extrema, of course we don't study how to find it because you're looking for nothing. When does a function have extrema? We have this extreme value theorem. The extreme value theorem says if f is a continuous function, we will study what this continuous means. If f is a continuous function whose domain is a closed interval, then f has an absolute maximum and an absolute minimum. Okay, if you have continuous function over closed interval, then you will have absolute maximum and absolute minimum. Continuous, that's a difficult concept to define so far, but basically continuous just means when you sketch the graph, you can start from one end, go to the other end without break. Okay, so continuous just means the graph is not broken. Okay, when this happens, the function always have absolute maximum and absolute minimum over the closed interval. So this is a continuity. Second important property is a closed interval. So with these two C words, continuous function, closed interval, then the function must have maximum or minimum, absolute max and absolute min. Okay, so we don't finish this section yet. We will continue the discussion in the next short video. After that, we will move to the next section. So this section is a long section. It has a lot of important properties. You need to do exercise to memorize those properties, and you should be able to examine and verify those properties. Okay, so we finish this section and continue in the next short section and next short video. Thank you.